Right, question number. Question number B. No. The answer is 19. Question number 19. Answer a mass of 0.05 kilogram connected to a spring with spring constant 60 undergoes simple harmonic motion on a smooth horizontal surface with an amplitude of 0.2. Find the maximum kinetic energy and maximum velocity. Yes. Simple harmonic motion, question number 90. Right, maximum kinetic energy. Maximum kinetic energy is equal to the maximum potential energy. So maximum potential energy is half Ka squared. Half K is spring constant 60. Amplitude is 0.2. One point two joules. 1.2 joules is the maximum kinetic energy. Then the maximum velocity is a omega. Amplitude 0.2. So what is omega? Omega of the expression is square root of K over M. K is 60. M is 0.05 mass second. So 6,000 over 5. 1,200 square root. Make n 400 times 2 n. 400 times 2 so 400 times 3 1,200. 400 square root is 20. So answer is 20 root 3. Which is I think 34.6 radians per second. 6.92 meters per second. 6.92. Sorry, 6.92. Right, then find the kinetic energy and velocity at the moment when it has displaced 0.1 meters from the center of oscillation. So kinetic energy when it has displaced 1 meters is this half m omega square. A squared minus x squared is the expression. Half m is 0.05. Omega is 34.6 squared. A is 0.2 squared. X is 0.1 squared. Like answer A. Velocity again, we have velocities. Take an expression, velocity is omega times a square minus x square, omega 34.6, a 0.2 square, x 0.1, 1 square. So around 3 and all, then 6 and all. Is it? 6 is coming. On the left, yeah, give me one second. 6 point. Right, question number 20 make it. No. Question number 18. So we did spring systems last week. Yes, sir. Spring systems करा रहे. आरे कर भी बार बैठा हूँ मैं. तो बैठे क्या? Right, question number 20. That's why 18. A figure shows a mass simple and connected by two identical springs, each with spring constant K on a smooth horizontal surface. When a small horizontal displacement is given to mass simple M and it is released, it undergoes simple harmonic motion, shows that the frequency of vibration is R. Famous springs there, you know. And there's a mass attached in between these two springs. This one is K1, the spring constant is K2. There's an equilibrium position. So then, what it has done, so they have displaced small, they have given small horizontal displacement to this mass. Make a body displacement of the may spring in the stretch may spring in compressed. Right? Now see this. Suppose the extension of the spring is simple x. The total force applied is capital F. Total force applied is capital F. Right. Total force is capital F. And then what are the forces acting on each of this spring? Spring. So this on this spring, the force is this spring exert force towards which direction? If you consider the forces on the acting on the mass simple M, right? So this spring exert a force in which direction? Right. So suppose it is F1. Since this spring has compressed, this one also exert a force towards this direction. So F2. So what can you say about the extensions of the extension and the compression of these two springs? Are they equal or not? Both these equal, right? So this spring has extended, stretched up to simple x distance, and this one also has compressed similar length, right? So what can you say about what is the relationship between these F1 and F2? What is the relationship between F1 and F2? By looking at the forces. Now this is at the equilibrium, this mass is at the equilibrium point. So F is equal to F1 plus F2. So F is, we can apply F equals Kx. F is given by minus K times X. K is the spring constant of equivalent spring of the system. F1 is minus K1x. Why we use x here? Because stretch the length that spring has stretch is equal to x. F2 is equal minus K2 times right. Compression is also x. Right. So this x will cancel. X capital. Negative sign negative make a better than marker. The equivalent spring constant is given by K1 and K1 plus K2. Like that, like the case where the springs are connected in parallel. If you remember, when the springs are connected in parallel, the equal spring constant is given by the sum of the spring constant of the two springs. Yes? Yes, you need to do that. Make now equivalent taken. So here, both the springs are identical. So K1 and K2 is equal to K. So let's take the equivalent is K dash. K dash is 2K. So frequency is 1 over 2 5 simple m over K over simple m. So 1 over 2 5. This is K dash. So equivalent K is 2K. Okay. This is the frequency. The frequency. Right. Correct. Right. Then the final question: when the mass M is connected separately to two different springs, which springs constant K1 and K2 allow to undergo horizontal simple harmonic motion? If the frequencies of vibration F1 and F2 respectively show that. So frequency of vibration F1 is given by this expression K1 over M. Right? So square this expression F1 squared is K1 over 4 pi squared times M. Like a 4 pi squared M. So K1 is 4 pi squared M F1 squared. First expression K1 similarly, you can get an expression for K2 also. What is the expression for K2? 4 pi squared M is same. Frequency is F2. Right? Then, so we have the equivalent K. Equivalent K is given by K1 plus K2. Right? So if you write an expression for the F, here you have the expression 1 over 2 pi 2K over M is the expression 2 pi. So if you square the expression, right? So this is the one you can get. This is the equivalent K. Make equivalent K. This must be not 2K. This must be K1 plus K2 equivalent again. K1 plus K2. So K1 plus K2 is equal to 4 pi squared M times F squared. So now you can substitute values for K1 and K2. K1 is 4 pi squared M F1 squared. K2 is 4 pi squared M F2 squared. 4 pi squared M F squared. Get term with answer. Final answer is F is F1 squared plus F2 squared. Right? Right. Question number next. 20. It is okay. 20. Right. Let's move to question number 20. Question number 20. Right. Question number 20. A wooden block of mass capital M connected to a spring with a spring constant simple K and placed on a smooth horizontal surface. A bullet of mass simple M traveling with horizontal velocity capital B hits the wooden block, gets embedded in it, and remains inside. At this moment, the wooden block with the bullet undergoes horizontal simple harmonic motion. Find the amplitude of the SHM. The wooden block and also there is a spring attached to it. So what happens? A bullet is fired towards the block of mass M. The speed of the bullet is capital V. The mass of the bullet simple M. So as soon as you have read this question, you may get an idea about what are the theories, what are the physics behind, what is the physics behind this. So after firing a bullet towards the block, bullet hits the block and embedded in it. So what is the after motion of the system? So bullet has embedded in the block, and so since initially the bullet has a kinetic energy, the system has a kinetic energy. So therefore, the bullet and block, the system moves with and speed of v dash. So how do you get that speed? What is the physics theory? Which theory you are going to use here? Conservation of linear momentum. So you need to put conservation of linear momentum by the principle of conservation of linear momentum. The initial momentum is mv of the bullet. Initial momentum of the block is 0. Final mass of the system is m plus capital M v dash. So v dash is the final speed of the system, which is simple mv over capital M plus simple M. Mass speed after the collision. Then what happens? After the collision, the system has a kinetic energy. So when this spring has compressed up to its maximum value, maximum distance, that kinetic energy has converted into potential energy in the string. It has stored the potential energy in the right? So what is kinetic energy? What is the expression for the kinetic energy? Half mv. Actually, M must be the capital M plus simple M. Right? Half capital M plus simple M times v dash square must be equal to the half a x square. Half a x square is the elastic potential energy. So kinetic energy must be equal to the elastic potential energy. Kinetic energy after the collision is given by this expression. Potential energy stored in the spring is given by half k x square. The question asks About the amplitude. Amplitude is, you can take it as A. So find A. Half cancel venom. M plus simple M. What is V dash? Well, V dash you know. Simple MV over capital M plus simple M square. So 1 M plus capital capital. So question final answer is you have MV square over capital M plus simple M. Take divide. This is A square. A is the square root of this. Square root of MV over A times M plus M square root. So that this is the answer. So in the answer, the same value should be simple M. Change into simple M. Answer can be capital M here. Right. Right, question number 23. Who got the answer for the question number 23? Anyone? You got? Huh? 26. Right. Look at the question number. So, hello, the question. 26 and 22nd. 23rd. Right. A YouTube with uniform cross-sectional area is placed with its arms vertical. A homogeneous liquid is poured into it. The total length of the liquid column is simple L. When the air pressure in one arm is momentarily increased such that the liquid level in the arm moves down and down a small vertical distance from its equilibrium position, then released, the liquid column undergoes simple harmonic motion. Show that the relevant period of oscillation is given by the expression. Given, right? We have a YouTube දෙකක් තියෙනවා. YouTube එකක් තියෙනවා. We have a YouTube. No YouTube එකක් තියෙනවා. Initially මේකට දාලා තියෙනවා liquid එකක්. Liquid එකක් දාලා තියෙනවා. Right? Suppose liquid is filled up to this point. The point there. So then what happens? When the air pressure in one arm is momentarily increased, the make arm make the air pressure increase. So what is the result? When the pressure increase, the liquid column in this arm will go up. So suppose the liquid column in the other arm has moved a simple x distance. The main level again. This is the level, initial level. This liquid column will shift down of distance of simple x. Simple x distance So what is the distance that liquid column in this arm will rise? Yeah, again x distance up. So what is the excess weight on the liquid column here? So the total length of the liquid column above the normal level is simple 2x. Make a 2x neither. 2x neither. Now we have this liquid column. So suppose the length of this liquid column, length of this whole liquid column is simple L. The sample liquid column make a length එක simple L කියලා ගන්න. එහෙම කියනවා. simple L කියලා දීලා තියෙනවා. Length of this like මොකදින්න ඔය බලාගෙන මේ වගේ questions MCQ වලට එන්නේ. Structure design होती है. මේ length එකම simple है. So now what can cause the restoring force in order to perform simple harmonic motion? You know, when there's a simple harmonic motion, when there's oscillation, there's always a restoring force to accelerate the body. So which force gives the restoring force here? Which force exerts the restoring force in order to take this liquid column up to equilibrium position? So actually, the weight of this liquid column, the weight due to the weight of this liquid column, the weight of this liquid column will exert. Weight of the liquid column gives the restoring force, right? So weight of the liquid column, weight of the weight of the liquid column is 2x. Suppose the cross-sectional area of the UTM is capital A, then the volume is here. Density, volume into density is mass. G, weight. Weight taken volume into density into gravity. Weight on a weight taken. So now you can apply F equals ma. Now we apply F equals ma. The restoring force is this force 2x A rho G. What is the mass of the liquid column? This force acting on which liquid column? This force acting on this one, this liquid volume. Right? So what is the mass of this liquid volume? The cross-sectional area is A. So mass is volume times density. Volume is cross-sectional area into length of the liquid column. AL times density of the mass second. So why we put the minus sign here? Because the direction of the displacement is opposite to the direction of the acceleration. Take this out. So rho will cancel, capital A also will cancel. Subject simple A, which is minus 2g divided by L times x. So can you recognize this expression? This expression looks like A equals minus omega square x. So omega is 2g over L square root. That is the omega. So question asks an expression for time period. This is the time period. 2g over L. So expression, final expression is 2 by L over 2g. L over 2g. Right. Note down. It's a good question. වගේ එකක් essay එකකට link කරලා දෙන්නත් පුළුවන්. right hydrostatics එක link කරලා දෙන්න පුළුවන්. surface tension hydrostatics ඔක්කොම link කරලා විතර දෙන්න පුළුවන් question එකක්. complete. Weight of the liquid column is the weight of the liquid column of this height. Two weights. Right? Right. Height into cross sectional area is the volume of the liquid column. It into density. Volume into density is mass. Mass times gravity. Right? Okay, now see the question number 24. 24. Similar kind of a question. You can try it now. How the answer not to make? You did not. Question number 24 is about hydrometer. Like I tell you, right? हम एक करा लीजिए कि यार ना कितना किलो बस बुला से एक डांट है, लेकिन कॉपी करना था, ना? और तुमने देखा था? Right, question number 24. So hydrometer, we use hydrometer to measure the density of a liquid. So this is the shape of the hydrometer. It has a stem of constant cross section, and end of the stem there's a large bulb. Like, yeah. So this bulb is filled with metal balls, right? It is not like a barometer. But you conical shape bulb. So this bulb filled with metal balls. Why is that? And its volume is very large. So we have a calibrated, graduated scale here. Scaling it has some strange thing on it. The scale again. Scale again gaps equal gaps densities equal numbers equal gaps hydrometer. Yes. Huh? No. Mercury no meeting. Make a empty void mercury is not a bar. Mercury mercury bulb mercury glass thermometer this filled with mercury. Mercury. Mercury I make a young red foods. What is the reason? Huh? In order to bring its center of gravity to the lowest point and to make sure the hydrometer is stable when it immerses in a liquid, right? Make a calculation and do a power in the in order to get the center of gravity of the hydrometer the lowest point. To keep the center of gravity and center of buoyancy closer to each other. Right? Make it body capillary slim stem make scale barometer tube barometer मैं क्या barometer आता है barometer क्या है मैं यहाँ की देख लेते हैं मैं विधि ट्यूब पे आती है ना 1 मीटर लेती है ना एक अपसाइड डाउन होती है मैं क्या आगे बराबर एक no this is hydrometer hydrometer used to measure the density of a liquid. Density කෙලිම observe කරන්න පුළුවන්. hydrometer එක නෙමෙයි question එකේ තියෙන්නේ. මේ වගේ hydrometer එකක් මේ විතර stable rod පේනවා. දැන් මොකද කරන්නේ? උඩින් පොඩ්ඩක් මේක push කරනවා. දැන් මේක balance නේ. මේක balance කියන්නේ upthrust is equal to upthrust එක තියෙනවම upthrust is equal to weight of the barometer. Now it's balanced. දැන් ඊට පස්සේ මේක උඩින් චුට්ටක් right. දැන් මොකද වෙන්නේ? චුට්ටක් පල්ලෙහාට මේක අල්ලු කරනවා. They have pushed this hydrometer into the water a little bit. Suppose it is distance of simple x. Simple x का distance එක පල්ලෙහාට දාන්න. මොකද වෙන්නේ? Simple x distance එක क्या? ගිලිලා very good. අනිත් කලින් දැන් මේ දීප level එක දැන් x distance එක ගිලිලා. So what is the result of this? දැන් කලින් දීප mark එක මෙතන දීප එක දැන් මෙච්චර distance එකක් වැඩිපුර ගිලිලා. So what is the as a result of this? An excess upthrust is acting on the hydrometer. Upthrust is very there's an excess upthrust on this hydrometer. Now the weight of the hydrometer, upthrust, initial upthrust is u. Now the excess upthrust is delta u. Right? Initial W equals u. Now what is the excess force acting on the hydrometer? And in the previous case, u equal W. Weight is equal to upthrust. Now the upthrust has increased about delta u. From delta u about. Right? So now what is the excess force or net force acting on this hydrometer in order to bring it to its equilibrium position again? W plus excess force. Excess force से कुछ चला. हम तो वेरी कुछ दिन वाले कुछ चले. खाली U equal W. तो मैं तो मैं खाली U. Now W. U plus delta U is the now total upthrust on this hydrometer. W minus delta U. W minus delta U. What am I going to do there? How do you get the net force? How do you get the net force? Net force is going to make difference. So what is difference? Net force is upward. So U plus delta U minus W. So what is U? Here U equal to W. So W minus delta U minus W. So the net force acting on the hydrometer is equal to the increase of upthrust. Delta U, the excess upthrust. Right? So this is the force which gives the acceleration in order to bring this hydrometer to equilibrium position. Acceleration again. Then again, like previous, apply F equals ma. Force is delta U ma. Now look at this. Tell me what is the excess upthrust? How we get it? Upthrust is 0 g. What is the excess volume? X into cross-sectional area of the cube. This is the volume. Rho is the density of liquid. G. So we put negative sign also here. So the acceleration is opposite direction. Ma. So acceleration is minus a rho g over m times x. So this is same expression minus omega squared is. So omega squared is a rho g over m. Omega squared is a rho g over m. I'll take the omega. Right here. Make excess upthrust again the pressure force again. Yes. Omega square is a rho g over m. Omega is a rho g over m square root. So T equals 2 pi over omega. T equals 2 pi over omega and omega becomes correspond to the Mega omega square correspond. Take a question example. Right, Adagan or like scenarios. Right, hi. एक बार कराना है इसलिए ये लेवल है Right. Then the second part is you need to have substitute values for t and okay. Let's do the second part. Second part of the question. Number 24, second part take on. Take a copy කරගෙන ඉවරලා second. මේ මම ප්‍රැක්ටිස් කරන්න අතරදාලා ඉන්නකෝ මේ question number 24 එකේ second part එක. When the hydrometer performs vertical simple harmonic motion in water, its period of oscillation is 2 seconds. If the period of this hydrometer in coconut oil is 2.1 seconds, find the relative density of coconut oil. Well, the time period of the hydrometer is given by this expression. For both these occasions, in coconut oil and in water, mass of the hydrometer, cross-section area, gravity, all these things are constant. Right? So T equals 2 pi m over a rho g. So 2 pi is a constant. Make up the situations they are equal. So that means the time period is proportional to the 1 over square root of density. Density is square root equal. Right? So time period of water is proportional to the 1 over density of water is 1000. Time period is 2 seconds. For water, for coconut oil, time period is 2.1 times density of coconut oil is rho. These are the two expressions. Divide them. 2.2 over 2.1 is equal rho over 1000 square root. Going to make a square and 2 divided by 2.1 square times 1000. Get the answer. Oh, yes, the constant. Yes. Two over 2.1, so you know 1 over root 1000 divided by 1 over root rho. Second part of this part. space of the right, that's fine. But you need to write an expression for the acceleration, not for the force. Acceleration must be omega squared. The omega is there, the k is not omega. You find the k value. All right, right. Fine. Fine. Next question. Next one is 25. Question number 25. 25 has a point, no? Right, question number 25. A simple pendulum is made by suspending a sphere of density D from a string of length simple length. Show that the period of its motion within a liquid of density rho is given by T equals this expression. Right, T equals, T is given by 2 pi square root of LD when making that. Right. So tell me how to initiate this question. From where we need to start? What is the first thing you need to do? The first step you need to follow. Question එක දැන් enter වෙනකොට enter වෙන විදිය මම කියන්නේ මොකද මුලින්ම කරන්න ඕනද? මොකද මුලින්ම කරන්න ඕනද? ඔයා නේ question එක හදලා question එකේ පළවෙනි step එක මොකක්ද? You need to draw a suitable diagram. First thing is you need to draw diagram. And diagram එකක් ඉන්නේ pendulum එකට. ඒ බලන්න. pendulum එක කොහෙද තියෙන්නේ? medium එක මොකක්ද? medium එක. is in a liquid. Right? එතන මතකද? Last week අපි කළා pendulum එක යාම තියෙනකොට which force provide the restoring force? Restoring force එක කවුද provide කරන්නේ? Weight of the component of the weight provide the restoring force, right? So make forces mark. So you have the weight of the pendulum, tension in the string. What else? Is that the only forces now? This pendulum is immersed in a liquid. Yeah, upthrust. So there's an upthrust. Upthrust is suppose this angle is theta, and also the alternative angles, this angle is also theta. Right? So you can resolve these two forces. Make mg force tangential method. Component of the Ng along this direction is Ng sin theta. Upthrust component U sin theta. So what is the net resultant force acting on the direction of center of oscillation? The net force is mg sin theta minus u sin theta. U sin theta. Right? जब भी अप्लाई करूँ तो equals I alpha. तो then start करें. Right. So torque is provided by the net force of these two. Sin theta is a common term में करने से ये लिखना होगा mg minus u times sin theta equals I. IL is consider this as a particle. Length of the pendulum is simple L. So moment of inertia is ml squared. Alpha is linear acceleration over radius. Radius is L. Right? This is came from A equals R alpha equation. A equals R alpha. So A equals L alpha. Alpha is A over L. MIR. අපි ගන්න ඕනේ linear acceleration and acceleration ඒක අරගෙන minus omega squared x කියලා පෙන්නන්න ඕනේ. acceleration එක minus omega squared x කියලා පෙන්නලා ඉතින් omega ගන්න ඕනේ. ඒක linear acceleration එක ඕනේ. simple harmonic motion එකේ characteristic expression එකේදී a equals minus omega squared x. එසා අපි simple harmonic motion එකක් මේක perform කරනවා කියලා පෙන්නන්නේ කොහොමද? එයාගේ linear acceleration එක හොයලා ඒක minus omega squared x type කියලා පෙන්නනවා. So now we are going to do that. Right? So බලා ගන්න දැන් හරි දැන් නිකන් ඉඳලා හරියන්නේ නැහැ මේ වැඩේ. Right. Then present tense note. Suppose the volume of the pendulum bob. Volume of the bob is capital V. Right? So tell me the expression for the mass of the bob in terms of capital V. Mass එක කොහොමද දෙන්නේ bob එකේ? ඒකේ volume එක capital V. You know the volume, how you get the mass? Mass volume into density. Density of the material sphere made is D. VdG. Up plus is V, density of the liquid is rho, V rho G. Since theta is very small, when theta is very small, so you can replace sin theta by radian theta. So this is radian theta. Mass of the pendulum bob is V times D. L එක cancel වෙනවා. Now from this expression you can cancel V also. Subject simple A. Simple A equals මෙතන G common term එකක් ගත්ත එළියට D minus rho over dl times theta. So now you can write this theta. Suppose this linear distance is x, the length of the arc is s. Right? So s equals r theta. S equals r is simple L theta. Since theta is very small, this x is approximately equal to the length of the arc. So x equals L theta, theta equals x over L. This theta is x over L. So A equals G times D minus rho over dl x. It is x over L. So dl එකක් කියනවා නේද? හරි නේද? question එකේ මොකක්ද තියෙන්නේ? L එක උඩට තියෙන්නේ නේද? Right. Dependent the potential. Theta is x over L. A over L becomes DL, right? Let's see. I got x over L. So A equals make x of insert x of the displacement negative one negative. So A equals minus G D minus rho into make up L square make up L. Come here check. This is the omega square. It's the omega square. Okay, omega omega. Omega make a square root. T equals 2 5 omega use करना expression ने done. But अगर L square का क्या है जो check कर. ताकि better L लेकर क्या ना. Better force से क्या लेकर तो should पारा. This is not the force. This should be a torque. Force से क्या L की value कराना नहीं है. अगर L की value करना है. Oh, take it down. Better L cancel लेना. L तो L cancel लेना. Better D L में. D L में. Then better X over L की L लेना better. Right. So omega is G over D minus rho over D. Make a square. T equals 2 pi over omega. 2 pi omega dl divided by G times D minus rho. Final expression. Right, copy करें याद है? Right. Right, अभी आपको में theory को डालने में मसला है। 6 से करें 26 से कितना होगा कंसंट्रेशन What is the one here? Finally, sketch the graph showing how the kinetic energy. Up here, the graph. Kinetic energy. Right. Right. So let's move on to the next part, which is about vibrations. Vibrations. So simple harmonic motion is completed. Now we are going ahead. The small things we need. Right, so let's talk about oscillations. Oscillations, right? So oscillations, we can divide oscillations into two parts, two types. Actually, only two parts, two types, right? So suppose there's oscillation. There are some oscillations, right? For example, think we oscillate a simple pendulum in vacuum. We swing a simple pendulum in a vacuum. So what will be the motion of it? Does it come to rest? No. Why is that? There is no resistive forces. If you displace the object or system, if you give a small displacement to object and release, then let it oscillate. So that kind of oscillation is a free oscillation. It is free oscillation. We equilibrium position like product displace we let it oscillate freely. So it is known as a free oscillation. A free oscillation. Initially we gave some displacement and release, then it moves. So it is a free oscillation. Right? So for example, the simple pendulum oscillates in a vacuum. So what can you tell about the tell about the energy and the amplitude of that motion? What can maximum amplitude? Maximum amplitude. What can you say about the energy? You swing a pendulum in a vacuum. What happens to its energy? Does it destroy? That's energy loss to any? No. It keeps energy. Yeah, same. The energy is same. No loss of energy because there's no resistive force. No work need to be done to oscillate. But therefore, the energies remain constant. And also, what can you say about the amplitude of the motion? If the energy is constant, the amplitude must be also the same throughout this oscillation, right? So, if we draw the displacement time graph, displacement versus time graph for this kind of a motion, it is like this. This one like this. The amplitude remains constant. No any decrease or increase of amplitude. The energy is right. So this is the displacement time graph for free oscillation. Free oscillation එක කොහොමයි වෙන්නේ? එයාගේ displacement එක වෙනස් වෙන්නේ නැහැ time. Now suppose we are swinging a pendulum in a liquid medium. Suppose we are going to oscillate a simple pendulum in underwater. Right? So what can you see what happens when you swing it. Up. It will come to rest at some point. Then after quite a while, it will come to rest. So because there are resistive forces acting on the pendulum, in this case, especially maybe a upthrust or viscous force there, drag forces there, viscous forces there. Due to those forces, in order to maintain its oscillation, pendulum need to do a work. Right? When you are doing work, your energy is losing. So there are more energies lost due to the work done against the resistive forces. What happens to the amplitude of the motion? It reduces. So those kind of oscillations, when the amplitude is gradually, or when amplitude is losing or amplitude is decreasing, energy is losing, right? These kind of oscillations are known as damped oscillations. Damped oscillations. What are the damped oscillations here? These are free oscillations. These are free oscillations. Like in a damped oscillation, the displacement versus time varies with this, like this. The damped oscillation, so it's like this. After a while, the amplitude gets zero, energy total, it loses its energy total. Right? A damped oscillation. The vehicle like a spring suspension system. Think about suspension system. The spring, the oscillations of the spring, is it a free oscillation? It should do free oscillations or damped oscillations. Free Yana kammo itin dekaya ayo wenne me iwar enne ned adisya genagawa metra wala gannu dewa gedara metra nawathot pahane vibratory right eka ihone damped oscillations la amplitude equally damped වෙනවා that is good නේ දැන් ඒ වගේ suspension system එක මෙහෙම damp වෙන එකත් අවුල ඕම කියලා ටික නම් ගොඩක් වෙනකොට vibration එක දැනෙනවනේ suddenly damp වෙන්න පුළුවන්. මොකද critically damp කියලා තියෙනවා damping methods තියෙනවා. ඒ වගේ වෙන්න ඕන. හරි මේක අපි errors වල සඳහන් කරන්නේ. So damp oscillation එක මේ විදිහට තමයි එයාගේ displacement එක time එකත් එක්ක amplitude එක vary. Actually this is the amplitude එක. Displacement ගන්න amplitude කියලා අපි ගන්නවා. Amplitude versus time. Amplitude එක. Amplitude will decrease. Right. So there are some oscillations called forced oscillation. Forced oscillation. What is forced oscillation? So in practical oscillations, practically oscillations are damped or free. Damped oscillation. Most of the oscillations we know they are damped oscillations. Practically. Vacuum මේකෙන් අපි මේ pendulum එක swing කරන එක practically real life එකේ වෙන්නේ නැහැ. Most of the real oscillations are damped one. Right? So in order to maintain the oscillation, suppose you need to maintain this oscillation for a quite a while, what you need to do? The oscillation එක ටික වෙලා තියාගන්න. Think about swing. Swing එකක් tonchillawක ඒ motion එක දෙකපාරක් පල්ලු කරොත් එහෙම it is a free oscillation එකක් මොනද එකපාරක් පල්ලු කරලා ඔය පැත්තට දුන්නොත් ඒක damp oscillation එකක් වෙනවා නේ damp oscillation එක natural oscillation එකක් it is natural but damp right so you need to maintain this oscillation throughout a certain time මොකද කරන්න ඕනේ oscillation එක දිගටම තියාගන්න මොකද කරන්න ඕනේ time සැරේට force එකක් දෙන්න ඕනේ. Force එකක් දෙන්න. Force එකක් දීලා energy එක දෙන්න ඕනේ. move කරන්න. අන්නේ motions වල ඒ oscillation අපිට force oscillations. They are force oscillations. In order to maintain the oscillation, Right? We need to give a periodic force on that system. The systems which is under influence of that periodic force called force oscillations. Right? Force oscillation. So those kind of oscillations also known as they are artificial oscillations. Those oscillations are artificial. These are they are natural oscillations. Natural, artificial energy. And energy to how many vibrate. So it is a natural oscillation. Force එකක් දීලා අපි මෙයා බලෙන් කම්පණය කරනවා. බලෙන් vibrate කරනවා. So it is a forced oscillation and it is also called artificial oscillation. Right? The frequency that body oscillate under this force oscillation, under this the force, a force of an operating force. But the frequency that a body oscillates in an artificial oscillation is known as artificial frequency. Artificial oscillation is the body oscillator frequency. Artificial frequency. Artificial frequency. So natural oscillation body oscillator frequency natural frequency. There are natural frequency and artificial frequency. They are. Pendulum initial displacement then frequency. So that is natural frequency. Now suppose I give force and repeatedly force this pendulum to move. Right? Now its frequency is artificial frequency. Right? There's a beautiful thing happens when this artificial frequency is equal, when the artificial frequency is equal to the natural frequency of that body. If the artificial frequency is equal to the natural frequency of that body oscillates with greater amplitudes or large amplitudes or maximum amplitude, which means that body absorbs maximum energy from the source. Oscillate maximum energy it oscillates with large amplitude. That phenomenon is known as the resonance. Resonance happens when the artificial frequency of a oscillation is equal to its natural frequency. Natural frequency artificial frequency equal. Artificially move oscillate frequency natural frequency equal. And very amplitude large amplitude oscillate. Right? That's what happened when the that's what happens when the microwave oven functioning. Microwaves are they use H2 water in the molecules. The frequency of the natural frequency of the water molecules are nearly or the approximately equal to the frequency of the microwaves. Microwave frequency water molecules frequency natural frequency equal. There are the microwaves make a incident but water molecules frequency microwave frequency equal. So water molecules are into resonate. They resonate with large amplitudes. Amplitude large, when you oscillate, the collisions, number of collisions between the water molecules are increased. The kinetic energy of water molecules are now uses as heat. Not the super question. They take same kind of a wave same kind of wave it's not a super question. Take a microwave breaking microwaves are water molecules artificially oscillate. The microwaves are frequency in the oscillate. Suppose the frequency of microwaves of 100 become 100 hertz. 100 hertz make a vibrate. The natural frequency of the water molecule is also 100. So both the frequencies are same. Artificial frequency and the natural frequency are same. So then the water molecules oscillate with large amplitudes. Right? If the frequency of the microwave waves are 50, natural frequency of the water molecules are 100, they also oscillate, but not in large amplitudes. We have oscillate with. Water molecules are natural frequency 100, CI. Microwaves of the know up to frequency 100 Hz. Like equal, have oscillate have large amplitudes there. Right? If you make to incident a microwave or some kind of wave is 100 Hz, which same as the natural frequency of the water molecules are. Here water molecules resonate with large amplitudes. They oscillate with large amplitude. That is resonance. What is resonance here? You can look at object that copy, force a vibrate karana a vibration frequency force vibrate frequency a frequency a body a system natural frequency equal 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 available equal body look amplitude so resonance. Mind that every object, every body has a frequency. That frequency is natural frequency. We also have a frequency. If the proper frequency is tuned, you also get oscillates. If it may be a 6-8 beat or is a beat again, you also get oscillates. Vibration frequency molecules vibration frequency. So that frequency is natural frequency. So this disk has a frequency to vibrate. If I provide a proper suitable energy to it, it oscillates. There are no energy to not oscillate. The pet me out of Hematia. Make a mother it oscillates. Pendulum. It oscillates. That oscillate that frequency is natural frequency. Natural frequency. Jab make a bomb him again oscillate karna, me oscillate karanga. Hear that? Then current bag, then make a mong aragana, then calling kare Himadila there. And the frequency that is natural oscillation. A frequency natural frequency. Then make a bomb him aragana. Oscillate karanga. The oscillation frequency, natural frequency equal. Then it get resonance. Then it is the resonance. You know that? Resonance. Then resonance now the branch branch so that's what happens. The natural frequency is equal to the artificial frequency. Then it resonance and breaks. Anyway, ये वेला दे cartoons ले मधी ना इधर opera sing करने को ये हमारा this लड़ी दे glass से touch कर resonance. The natural frequency of the glass is equal to the artificial frequency. Breaks. Samar do it the way. Thundering बोले दिए ना glass जब windows से हम cracks हैं नहीं. हमारा ना दे दो ना नहीं. Vibrate ला यार हमारा. That is resonance, due to resonance. The bus say engine and what tune slow a glass is resonance. Resonance. ये practical applications नहीं होता मुझे में ये वो practical resonance वाले application है practical situation ने का क्या लाती है ना 1940s वाला Tacoma Bridge of USA internet के बारे में क्या Tacoma Bridge Tacoma Bridge make a swing bridge make a construction इधर कर ला मैदाने within 1 or 2 days one वाली make a उलंघन wind कटा make oscillate पेला resonance पेला Chris troll है एक वीडियो कर दिया ना मतलब स्विंग में ना मेरे नाम दिया था मेरे टैगो ब्रिज एक अब करते हैं उलंघन है हिंदीला पहनतीला एक उलंघन साइन एक फोर्स oscillation ने का एक artificial oscillation ने का आगे natural frequency के लिए equal ना एक बार इक्वेट चला तो उन्हें कहते हैं कि हर natural frequency का बड़ा जाता ना तो आटे आवर resonance कराना होगा ठीक है दायरे तो resonance सुनना होता है ये लेवल पे क्या होता है ये अलग frequencies वे दिए ना हम देख रहे हो दिए ना ये connections अभी भी अभी डील कर नहीं होगी frequencies से कहने के माइंड देखा भी किया अभी देवा फिर देने ना अभी तो ये frequencies से क्या right so when if the two frequencies are the same then both of you can resonate ready amplifying and right so you can extend maximum energy between both of you right so that is resonance when right when a body resonates this is how its amplitude change right so this is how its amplitude change in the frequency this frequency is artificial frequency this is amplitude when body resonates its amplitude so amplitude get maximum when artificial frequency is equal to natural frequency. Right? So every object has a frequency, natural frequency, and not only one frequency. They have a series of frequencies. Natural frequency series से करती है, एक frequency का नहीं है, right? The smallest natural frequency is known as fundamental frequency. Fundamental. The smallest natural frequency is fundamental frequency. You know that. The second natural frequency is known as first overtone. First overtone. Fundamental. The second natural frequency, second highest natural frequency is first overtone. The third highest, second overtone. Fourth highest, third overtone. And we have overtones. Frequency series here. That's it. So then again, what are the pre-oscillations? The oscillations which is undergoing without any resistive forces. Pre-oscillations. Right? Damp oscillations under the influence of resistive forces. Amplitude decreases. Right? So if we provide a periodic force to maintain that oscillation, so those oscillations are forced oscillations and also known as artificial oscillations. Right? When the artificial frequency of the oscillation is equal to the natural frequency of that body gets resonance. It resonates. Right? When the resonance occurs, the body absorbs maximum energy from the source. Source can oscillate. It absorbs maximum energy. You know that maximum energy it absorbs, and amplitude is the highest. Right? Value amplitude taking from it is the highest one. So that is known as resonance. There are not only one natural frequency for body, there are series of sequence of natural frequencies. The lowest one is fundamental frequency. Next, first overtone, second overtone, like that. Right? So suppose the first overtone is 2 times of fundamental frequency. Right? A given overtone is how much of the fundamental frequency means, yeah. That's a standing wave. It's not greater this that is only standing waves. ඒවත් overtones ගැන කතා කරනවා. They are the fundamental, and those are the natural frequency sequence. This is generally this is valid for all the tubes and strings and all things. All the bodies, all the oscillating bodies. It may be oscillating in air column, it may be oscillating in string, whatever. You know that. one can fundamental monari overtone එක fundamental එක වගේ කොච්චර times එනවද කියන එක. Is known as harmonic number. Right? If the fundamental frequency is 100, first overtone is 300. What is the harmonic number of first overtone? 3. Yes. Seismic waves. The seismic waves are the waves which generate earthquakes. When earthquakes happens, they are the waves carries that energy. There are two types. Surface waves and body waves. Surface waves also can. There are several types. Rayleigh waves and long waves. Body waves are 2 types, S and P waves. Right? So now we come back to that piano at the waves. Now we are at the oscillation. If the fundamental frequency is 100, suppose the frequency of the first overtone is 200. So what is the harmonic number of the first overtone? Harmonic number means the given overtone is how much of the fundamental. First overtone is 200, fundamental is 100. So harmonic number is, it is second harmonic. First overtone is the second harmonic of fundamental. You know that? Harmonics can fundamental tone frequency. Overtone frequency. How much? Time? That is known as harmonic. Terms only. When we are dealing with the waves in strings, standing waves forms in a string, standing waves forms in tubes. We use these harmonic numbers, overtones, and natural frequency, resonance. Those words we often use. Right? So that's when these terms are significant, right? Topic The first topic is free oscillations. Free oscillations. Free oscillations. Free oscillations within brackets, natural oscillations. Free oscillations within brackets, natural oscillations. right under it. When a system is displaced, when the system is displaced from its equilibrium position, when a system is displaced from its equilibrium position and released it performs a pre-oscillation. It performs a pre-oscillation. The frequency of the pre-oscillations or natural oscillations is known as natural frequency. In an ideal environment, in an ideal environment, without friction or air resistance, the system will oscillate infinitely with constant amplitude and mechanical energy. Constant amplitude and mechanical energy. Example of free oscillation. A simple pendulum swinging in a perfect vacuum. Right. So the amplitude versus time graph. Of pre-oscillation. Right. Amplitude versus time graph for natural oscillation. Amplitude against time graph for natural oscillations. The topic is damped oscillation. Damped oscillations. Damped oscillations. These are oscillations. These oscillations are. Sorry. Increase the temperature. Increase means you need to is of 30 Celsius. Either one is it. Popular. මේක මට දාලාද? ඒකේ වෙට්ට නැති විදිහ නෑ. ඉතින් ඒක ඉන්න එක මේ බෑන්ඩ් එකක් වගේ එකක් නෙවෙයි. ඒක පොට්ලි මේකට එෆෙක්ට් වෙන එකක්. ඒක තමයි 20 ඒ දැන් ස්වීට් එකක් අරන් කලින් පස්සේ right upon the damped these oscillations are subjected to resistive or dissipative forces. Dissipative forces. Dissipative forces. Within bracket, like air resistance, friction, or internal viscosity. Next paragraph. Because of work is done to overcome these resistive forces. The system continuously loses energy. So therefore, amplitude of the oscillation decreases exponentially. Right. So this is the amplitude against time graph. Go it again. The next topic is forced oscillation. Forced oscillations. Forced oscillations. Forced oscillations. To prevent an oscillating system, to prevent an oscillating system, to prevent an oscillating system, to overcome these resistive forces, a continuous time varying, a continuous time varying external forces applied the system is forced to vibrate at the frequency of the applied force rather than its natural frequency. These oscillations also called artificial oscillations. The frequency of oscillation is called artificial frequency. A body has a sequence of series of natural frequencies, not a sequence. Series of natural frequencies. The smallest natural frequencies, called fundamental frequency. Rest of the natural frequencies are overtones. A big example here. Frequencies. Okay. So this is known as third harmony. Right? The ratio of the overtone frequency to the fundamental is known as harmonic number. Right? Harmonic number is the frequency of the overtone or fundamental frequency. Harmonic number. So what is the harmonic of this? Harmonic number of this second overtone? 4. Frequency of the overtone divided by frequency of fundamental. This one is 5. This is fifth harmony. This is fifth harmony. This is seventh harmony. This is seventh harmony. Yeah. Right. This topic is resonance. Resonance. Yes. No, the resonance of it. Resonance. 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 Right under this resonance. Resonance. Resonance is a phenomenon Resonance is a phenomenon. Resonance is a phenomenon in which resonance is a phenomenon in which a system vibrates. Resonance is the phenomenon in which a system vibrates. Resonance is the phenomenon in which a system vibrates with maximum amplitude. With maximum amplitude. Resonance is the phenomenon in which a system vibrates with maximum amplitude. When the frequency of the frequency of the external periodic force becomes equal to the natural frequency of the system. Natural frequency of the system, right? Yes, our particular characteristics of resonance. Characteristic of resonance. Characteristic of resonance. Characteristic of resonance. First one is amplitude becomes maximum. Amplitude becomes maximum. Energy transfer is maximum. Energy transfer is maximum. Occurs when natural frequency, occurs when external, occurs when frequency of the external force. Occurs when frequency of the external force is equal to the natural frequency right. So here's the amplitude versus artificial frequency. This one. Yeah. Start from 0. Examples of resonance. Examples of resonance. Examples of resonance. Examples of resonance. First one is a child on a swing. A child on a swing. A child on a swing. Second, vibrations of bridge. Vibration of bridges. Vibrations of bridges. Vibrations of bridges due to marching soldiers. Marching. The soldiers the bridge they will march so they are the rhythm vibration bridge natural frequency equal with them vibration vibration of bridges due to marching soldiers. Air column in musical instruments. Air column in musical instruments such as flutes and air column in musical instruments. So, simple harmonic motion and vibrations part is over. Right? We have 7 minutes of time. Brain boost paper 23. Questions discuss kare naya man nikalne. But brain boost paper 23 then come here. Right. So, sharp when the event